communication overhead reduction using static analysis.
Yeah,
So, both English.
It's a pretty big title. I couldn't come up with a better. So basically, I'm going to talk about static analysis, how you would use that to reduce communication overheads. So it's a little brief agenda. I'll basically introduce data flow analysis really briefly. We'll see like there are two approaches to it, and then I'll go and talk about the optimization framework that is being used to reduce the communication overhead. Finally, I would like to discuss about verification. So I say discuss because I would like some inputs on it. I'm not really sure how to go about this. In fact, I haven't implemented any of these optimizations right now. I'm planning to implement them this way. So any feedback on that is also appreciated. Okay. So the first thing is, what is data flow analysis? Data flow analysis is a technique used by compilers to see what kind of values reach certain points in the program. So what you do is you form a control flow graph where everybody is okay with that kind of stuff. Like, is everybody aware of what control flow graphs are? Okay. So the control flow graph tells you how control flows in the program. So take for example the procedure. You have a certain entry point, then you have if statements, for statements, while statements. So for example, in an if there is a branching, right? Okay, I can just write it. So it's something like you have a starting point. Then when you encounter a loop, you'll have an if statement. You have a branching. If you again, then you might encounter a while loop where you have something like this, and it goes again back to this. So you can identify while loops and if statements and some basic blocks. So a basic block is basically a straight set of instructions. You don't have branching over there, you don't have looping. Okay. And this is inside a single procedure. You can have like this in multiple procedures also. So you form a control flow graph. Then what you do is you define what you mean by values that you want to compute at a certain point. So you cannot compute arbitrary values because we know that that problem is undecidable. Okay. So what you do is, for this to be sound, you have what is called a lattice. So again, so if you wanted to compute, for example, what kind of integers reach a certain, what kind of, so there is an integer x, and you want to know what is the value of x at a certain point in the program. So what you do is you form this lattice where this is like -1, 0, plus 1, blah, 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 blah. So there can be three possibilities. Either it is something from this side, right? Or you don't know, in which case it is top. And you know that it is not an integer. So if you don't know the type also. So you don't know it is not an integer itself. So these can be three values. And you form a lattice out of that, which is a partial ordering. And also you have a finite height to the lattice. And as I will discuss, like the set of values that this particular variable can hold, it cannot shrink. It has to stay the same, or it can grow as you simulate the data flow equations or the control flow graph. Okay. So there are two approaches to data flow analysis. One is iterative. As I said, you form a lattice. you set up data flow equations that approximate the behavior of what you want to do on the control flow graph, and then you iterate over the control flow graph. So again, you take something like so you have a particular function which simulates what you want to do. So you start maybe like in this order. You apply that function to this basic block. Again, then this. So then you apply it to this basic block, these two blocks, and in a loop, when you come here, what happens is you apply this to apply the function to this basic block, But then again, because of this back edge, these values, the values that you computed for f at this point might change. So you again have to recompute them at the loop position. So that is, and this is done iteratively. Okay. Now because the lattice height is fixed, and because the set of values that you are computing cannot shrink, it has to hit a fixed point somewhere. Yeah.
So when you say the set of values cannot shrink, do you mean it can only move like down the lattice?
No. What I mean is like lattice can be arbitrary height,
Okay.
but it is a finite height,
Okay.
and so the set of values that a variable take from this lattice, they can only grow.
Okay. But does that have any relation to going up or down the lattice? I think you cannot go down the lattice.
The way you described it, your lattice things flow this way. More information is this way, so you can only go down. You start with everything at the top, and then as you get information, you update the values, but you can no longer, once you commit to a certain value, you cannot go back and retract it. So you keep going and hit a fixed point.
So everything is unknown at the start. So you initialize it to top, and then if you can decide that it can take some integer value, then you go down. But you cannot again go to top. Right? Okay. So that was iterative approach, and we know that it hits a fixed point, so it stops. Another one is what is called a structural or interval-based approach, where you take in account the structure of the CFG that you have created. So, for example, in the iterative approach, you do not take into account that this is actually a loop, or this is actually a loop, or this is an if statement. What you can do is you can merge this region into one block and call it if then else. So basically you are abstracting these nodes out, then again a loop, and then finally you can merge the whole thing down into one block. So this is the abstraction of the entire program. This is the abstract node, and this, so you go back here, so this basically forms a tree like that. Okay. Now what you do is you start with the basic f functions here and you compose them. So for example, you have f then and f else here. You can compose them to form something like f then dot f else, and that is the compose function that will be applied on this abstract node. Finally you will get one function which is like the approximation of the entire program. Okay, so you do that in one pass. Now you again put in values. So for example, you can start with, suppose x is an integer you know, then you can start with the set of z for x. Then you apply these functions to those values to finally compute the result. So that is a downward pass. So you are done in two passes, basically. But as far as I can tell from the literature, they are saying that iterative analysis is easier to implement than this, and in practice iterative analysis is as fast as the structural analysis.
Can I ask a very simple question? What are you achieving?
So you're computing. So what do you mean?
Like, what does this whole thing do?
So this thing is so for x you are taking some values, right? And then you are applying the approximation of the program over those values as you go down the tree. Okay. So this is basically like passing values here, approximating these things, and finally coming out with a particular result for x.
The problem is that iterative solution, you can go forever. Not forever, but you can iterate for like half an hour, going a million times. And this way you build an abstract program, execute once a week.
Yeah, it is certainly faster, right? Because the iterative approach can take like a lot of steps, but this is just one pass upwards and one pass downwards.
Go on.
So that was a little brief introduction of data analysis. So for our optimization, we're going to stick to this particular example. You can see that it's an interval tree where, so this is a CFG, but they have approximated the loops as an interval. This is a loop, this is a loop, these two are again loops, and you can see that there is a header node to the loops, and there is a unique last node for the loop. This is important because sometimes loops can branch out in many ways to many locations, but here there is only one backward edge to the header. That helps in some further analysis, as we'll see. What is happening is x is getting updated here, referenced here. Similarly, y is referenced here, z is referenced and updated here. You can see that there is a true dependence for z. So some value is computed and then that is being used in the next iteration. Okay. What else? So those are some of the things that we need.